All right, my computer did not break, so let's do this. So, what are vectors? So, there are some technical, like some mathematical technical definitions. Um, so in math, you might hear, "Oh, a vector is, an element of a vector space, or it's a rank one tensor." We're not going to worry about that right now. Um, that's only really important for yeah, not this. So we're going to use the dumb physicist definition of a vector is any quantity that has both a magnitude or an amount and a direction encoded into it. So an example, all right, so an example of vector like quantities, vector space for point. Yeah, that's why I'm not worrying about the math definition today. So, examples of vector-like quantities, quantities that both have direction and magnitude. Um, we can start with velocity. So, whenever you're talking about your velocity, which is different from when we talk about speed, when we talk about velocity, we want to tell someone not only how fast we're going, but in which directions we're moving in, right? So if I say I'm moving at 35 miles an hour east and 25 miles an hour north, that can tell you that A, I'm moving northeast in total, and that I'm moving more east than north. Um, so this can help. There actually are a lot of quantities in physics that require both a direction and a magnitude in order to be able to accurately describe. Um, this is in contrast to what are called scalars. Oh, that's much better. Okay. Scalars are any quantity that just has a magnitude, an amount to it. So this would be stuff like mass or time or even it's another one you see every day. Or like yeah, even technically even money. Money is a scalar quantity. Okay, the Higgs field yes, we can also consider ass a scalar. There we go. Ass is a scalar quantity. Because the only thing you need to describe those units are just how much there is, right? So if I want to talk about how much mass I have, I don't know how much mass I have in kilograms off the top of my head, but I would just say that my mass is, say, 50 kilograms. It doesn't matter, like, it doesn't matter what direction I'm facing. That doesn't change that I just have 50 kilograms, right? It doesn't make sense to say I have 50 kilograms northeast or whatever. Same thing with time, right? If I start and stop a stopwatch just to like say measure a race, then I would say that, oh, let's say they did it in 70 seconds. Again, that's all the information I need to accurately describe how long it took for that person to finish that race. That means if I just say, oh, it took them 70 seconds, that's all I need to say. So these quantities are called scalars because they don't have a direction to them. So, um, let's all right. So, yes, so different, so different units will change the specific number you're talking about. So well, okay, pounds and kilograms is a bit of a tricky one to talk about because technically speaking, pounds is a unit of force, not mass. Even so, force is a vector. So if you're strictly talking about pounds as in force or weight, that is in fact a vector. But if you're saying like, so the imperial unit, so fun fact, the imperial unit or the American unit for mass, so I'll use square brackets to represent the units of some quantity, is the slug. So, in that case, the only thing that differentiates between me saying my mass in slugs versus my mass in kilograms is just the amount. And I don't know the exact conversion rate off the top of my head, but that's still, they're both still scalars. Um, so yeah. So why do we care about vectors? Why do we want to make math more complicated than it has to be? Um, First of all, it can simplify a lot of equations. So instead of having separate equations for talking about my position in the x direction, or meters, and my position in the y direction, I can instead just say, oh, this is in total a vector that goes northeast. Um, and I'll talk about how to actually represent vectors in a little. Yes, the y direction. Um, all right. So next part, how do we represent? How do we draw vectors? So, um, let's start with graphically, right? So that's why I have graph paper. So if I draw some axis, and let's say that each of these major divisions is 1 centimeter. So then if I want to talk about um, a displacement, like I want to move one, or let's say I want to move 5 meters north, exactly northeast. Then what I'd want to do is, all right, yeah, oh, all right, 500. Pen tool. There we go. All right. So let's say, no, hang on. I'm gonna redo the example. All right. So let's say this is our axis. Then, if I want to draw a vector, or a vector to represent a a displacement that I move. Let's say I want to move 3 centimeters east and 4 centimeters north. Then there are two ways I can draw that. So I can do, one way is component wise, right? So I draw out 1, 2, 3 centimeters east, and 1, 2, 3, 4 centimeters north. Centimeters, whatever. 4 meters north. And going from my origin, wherever I start, to where I end up becomes the total vector magnitude, right? So that also, once I have this drawn, that also allows me to designate some angle with respect to the x-axis, right? So this tells us that there are two main ways to represent a vector. I can either talk about, I can either say give its total length, which is 5 meters, and the angle with respect to the x-axis, which in this case is not 45 degrees, 60 degrees, I think. So I can either say this, I moved 5 meters at 60 degrees northeast. That is one way to describe it. Or I can mention the specific components, right? I moved 3 meters east and 4 meters north. Um, so this kind of lends itself towards how do we write out vectors if we don't want to talk about graphically. So what we can do then is I'm going to use A to represent my total displacement. So whenever you write out a vector quantity, you want to distinguish it from just any other scalar quantity. What I do in practice is just draw a little arrow on. And since and I can write this out in component wise, right? I can say I move 3 meters east and 4 meters north. And this x hat and y hat are called unit vectors. Unit vectors unit vectors are any vector that specifically has magnitude 1, right? So the magnitude or length of a vector is usually denoted by absolute value brackets. So the length of this vector A is 5. So that means that the magnitude of unit vectors by definition 1. And specifically x hat and y hat refer to unit vectors specifically along the x direction and y direction. So those allow us to decompose our vector into specifically components along the x-axis, components along the y-axis. That fairly coherent. So all right. Yeah, yeah. You don't count Ash. Sorry. Um. So yeah. Although actually, sorry, I take that back, Astral. That actually does help. If another physicist can follow me, that means I'm not getting it completely. Um. So, um, next, let's say we want to determine. Let's say we want to convert from talking about a vector in component form to our length and direction form, right? So this part unfortunately requires trigonometry because if you've noticed, let's use a different color. Where is the color on this? I know. It's fine. I'll walk you through how to do as soon as I figure out how to do. Really need to switch. I am really. Oh, wait. Fine. All right, whatever. All right. So, if you've noticed, if I have this length, how did it become? Okay. So, if you've noticed, this forms a right triangle with the x components, the y components, and the magnitude. And we know this is a right triangle because the x and y directions are perpendicular. They form a 90-degree angle. So that means if we want to convert from component form to magnitude and direction form and vice versa, we need trig. Yes, Tyler, exactly. So if we want to calculate the magnitude of A, then because this is a right triangle, we just need to use Pythagorean theorem. It tells us that A, the square root of the x component squared plus the y component. Because I picked a 3, 4, 5 triangle, yes, the bean. That's right. I forgot he had a bean cult. Yeah, Pythagoras was weird. Um, yeah. So we have the magnitude, but we still need to preserve the direction information. Fortunately, if we look at this angle, the 4 and the 3 form the opposite and adjacent angles um, to the right triangle for this angle. That tells us if we go back to our SOHCAHTOA, so opposite adjacent corresponds to our TOA. That tells me that tangent this angle. So if I do arc tangent or inverse tangent of both sides, that tells me that theta equals tangent inverse 4/3, which I'm going to plug that in. Yeah, okay. So that ends up being 60 degrees. And I'm going to stick with degrees for now, even though in physics we tend to use radians. But that's just because I don't want to go into the unit circle right now. So we're going to stick with degrees. So yeah, so that's how we would convert from component form to direction to magnitude and direction form. So now, if we want to go the opposite direction, let's say that I have been given instead the magnitude of A and the direction 60 degrees from the positive x-axis. Then I can still use trig to get back the component form. So if I look at the x component, this is the adjacent side to theta. So that means that if I do adjacent hypotenuse, sorry, then that corresponds to our ka, so our cosine. Yes, going if you have an answering component form, you want to double check, then doing the inverse calculation to make sure you get back the original vector is a good way to do what's called a dummy check. So yes, Cyrano. Um, so yeah, so this x component is our adjacent side, so that tells us that cosine of theta equals adjacent side. So let's do ax for 5. So the reason I didn't specify this, I'm just using little a sub x to represent the arbitrary x component of our vector a. So if I multiply on both sides, I get ax equals 5 times cosine 60 degrees, which ends up working out. And then for the y direction, this is our opposite side, which means if we go back to SOHCAHTOA, that corresponds to sine. So then sine of our angle theta equals our y component over the magnitude. That tells us that ay 5 times sine of theta so that is typically how you represent vectors, at least in 2 dimensions, and how to convert from the two primary ways to represent them. So I did these examples in 2 dimensions, x and y. Both of these work in 3 dimensions, although doing the length and direction approach in 3 dimensions just requires one more angle to determine the direction. But it's still ultimately um so any questions from this point onward? So I just wanted to do this just to be thorough, but for most calculations, or pretty much all algebraic calculations, it's much more beneficial to express the vector in component. So that's what I'm going to be doing from now. Okay, so hide that. And also, I will say, the other reason that I'm like just hiding these layers is in case you guys want, I am thinking about exporting these sheets later and posting them in my channel or something. In case you guys want to come back to them. So yeah. Next, we need to talk about the kinds of algebraic operations on vectors. So, first one, pretty simple, addition. If I have two vectors, let's say 3x plus 4y, let's use our original vector. And let's say I have some other vector, say 5x plus 7y, right? Then, if I want to add them together, at least in component form, this corresponds to just adding our individual components together. This is going to be 8x plus 11y. So, pretty straightforward, right? So, just take the corresponding components, add them up. Again, yeah, vector addition, pretty straightforward. You can do the same thing with subtraction. So, because if I want to do a minus b, this is the same as saying a plus negative b, which is just multiplying -1 times vector b. So this then corresponds to 3 minus 5x plus 4 minus 7y, and this would end up equaling negative 2x minus 3y. So yeah, addition, subtraction, fairly straightforward. There's not really much to expand upon when it comes to addition and subtraction. You can't add vectors of different dimensions. So for instance, if I had a two-dimensional vector and a three-dimensional vector, I just can't add them together unless I express that 2D vector in 3 dimensions. It's a bit more of a nuanced difference. So what's really different though with vectors is multiplication. That's where things get a bit more advanced. So vectors allow for 3 different types of multiplication. You can have multiplication by a scalar. So if I have just some number a and some vector a, big A, then I can just do a times a, which is equivalent to, if I use the original the vector a, it's going to be, I just multiply each component by the scalar. Right? Scalar multiplication, again, also pretty straightforward. That's how we were able to do the minus b. Minus b is just the same as doing minus 1 times b. That's multiplication by a scalar. Kind of like a special case of it. So, ah, so an important property of scalar multiplication that we should take note of is that it is in fact distributive over addition. If you don't remember the distributive property from grade school, what that means is if I have two vectors, a and b, and I want to multiply their sum by some scalar a, that is equivalent to a, not a unit vector, plus a times capital B. So scalar multiplication, it's associative. Um, by that I mean, yeah. So I guess it might be worthwhile to actually like wrong layer. There we go. So scalar multiplication, it is associative, and what that means is if I have two scalars a and b, then a b times a, doing the a and b multiplication first, is equivalent to a times b a. Like, yeah, it's associative. We talked about distributive. The distributive property, it is commutative, which just means that a b a is equal to b a and a b whatever. Those are all equal. Scalar multiplication, again, fairly boring, fairly straightforward. Now we get to these new kinds of vector multiplication, or the new kinds of multiplication that you might not be familiar with. So, vector addition allows for two other types of multiplicative operations, one of which converts two vectors to a scalar, the other one converts two vectors to another vector. And those are called the dot product and vector and cross product or vector product, respectively. So let's start with the dot product. The dot product is represented by the operation dot a dot b. So, and the way to calculate this is just to multiply um, their corresponding components together. AX EX plus AY. And as you can see, um, this takes two vectors and outputs a scalar because there's no unit vectors. And the reason that is because actually it'll be easy to show it with this other formula. So another way to calculate dot products, so A dot B is also equivalent to the magnitude of A times the magnitude of B times cosine of the angle between them, the angle between vectors A and B. So so then that means that if I want to do x hat dot x hat, well, as I said before, unit vectors have magnitude 1. That's 1 times 1. Cosine, since it's the same vector, it's just cosine of 0. Same thing with y hat dot y hat. That also means that if I want to do, say, x hat dot y hat, their magnitudes both 1, but x hat and y hat are perpendicular. That means that's cosine of 90 degrees is 0. So the dot product in that sense gives you a measure of how parallel two vectors are. If two vectors are completely parallel, then their dot product is maximum because that cosine is 1. Because if you remember from trig, cosine goes from -1 to 1. So in terms of just the magnitude of the dot product will be greatest if the two vectors are either parallel or anti-parallel, which means that you get cosine of theta equals -1, and their minimum, they're perpendicular. You get cosine. So, what properties does this dot product? Because the dot product takes two vectors and outputs a scalar, there is no associativity for three vectors because you don't get another vector to dot with. Um, Instead, you have associativity across the scalar multiplication. Um, the dot product specifically is commutative, and what that means is A dot B is equivalent to B dot A. And you can see that here, right? A dot B is AX BX plus AY BY. Since these are just numbers, these are scalars. Scalars are, of course, commutative. So I can swap their positions, and I just get back B dot A. So yeah, dot product is commutative. Um, it is also distributive across addition, just like scalar multiplication. So that means if I have A times... Sorry, no. It's about scalar. Sorry. If I have A dot E plus C, this is equal to A dot A. That's what it means to be. Any questions about the dot product? That one might be a bit new. I wish I had text to make catching questions. All right. Now, here is the annoying the cross. As I said previously, this operation takes two vectors and outputs another vector. You keep saying that, Astral, and now I kind of want to make it a point to lose you. Point. I'll probably get to do that with my laser talk. Um. Anyway, so this is denoted again fairly self-evidently by A cross B. So the way to one way to calculate this is by taking magnitude of A times magnitude of B sine theta times n hat, where n hat is a unit vector that is perpendicular to both A and B. That means that I've never been good. So if I have some 3D space, right, and I have vectors in the xy plane. This is x, y, a, b. Then a cross b is going to be along the z because z is perpendicular to the xy plane. There is another way to calculate the cross product by components, but this one is a bit more involved. So let's say I have two arbitrary three-dimensional vectors, right? Ax, x hat, ay, y hat, plus az hat. And same with b. Bx, x hat. Then what I can do set up this sort of matrix of the components. And what I can do is, so for the x component, I cross out the column and row that contains x hat. And then I multiply ay times bz, and then minus by times az. This is your x component. Then I would do for the y component minus, and then cross out this column and this row, and then I have ax e minus ex az y hat. And then finally, for the z component, it's ax y minus. So yeah, if you only had 2D vectors, so just ay b or ax b ax ay bx by, then as you can see, these two components would go to 0, and you're just left with this. So that's what I said, or that's what I meant when I said that cross products are a bit more complicated, because you have to take two vectors and output a third vector. And as you will see shortly, it does not like to play by the same rules that the dot product does. What I mean by that is cross product is distributive. Start out with. So, I have A cross plus C. That is equal to A cross B. However, it is not commutative. Which means that A cross B is not equal to B cross A. In fact, A cross B specifically equal to minus cross. So in that sense, it's called anti-commutative. And so a result of this kind of not commutivity means that you get a sort of handedness out of the cross product. And what I mean by that is you can kind of determine at least the direction a cross product will go by using what's called the right hand rule. So if I have vector A and vector B, if I start by taking my hand and pointing my 4 fingers along A, and I orient my hand so that I rotate my fingers as if I'm going to make a fist towards B. I know this is very hard to do with a VTuber. So if I curl my fingers towards the direction of B, whichever direction my thumb points is where the cross product will go. So in this case, I have to curl my hand counterclockwise, which means my right hand's thumb point up towards the positive Z direction. That also means if I were to do B cross A and I start at B, I would need to point my hand down in order to curl my fingers towards A, which means my thumb would point down towards the negative Z. Again, that is very hard to show with a V2 model that does not have hand tracking. But hopefully I make it work. Okay. So, going back to I've seen with the, are you talking about like the 2 fingers, whichever way the thumb's going? I learned it that way too, but I've just found it intuitively easier to do it with the whole hand. That's just a personal thing for me. Um but yeah. So going back to this this equation. If I want to find the magnitude of the cross product, then I can go back to AB sine theta. Because again, remember, where it had the n hat, the magnitude of any unit vector is 1. So that means the magnitude of the cross product is just AB sine theta. This tells me that in contrast to the dot product, the cross product is maximized when my 2 vectors are perpendicular. Because sine is maximum when theta equals 90 degrees, and minimum when theta equals 0 degrees. So this, in this sense, gives a way to express how perpendicular 2 vectors. That also tells me that if I want to do A cross itself, then that gives me magnitude of A squared times sine of 0, which is 0. So any vector cross itself is 0, or specifically the 0 vector, which is just 0 along each. Um, yeah. So we're hitting close to an hour, and I've kind of covered very conveniently, I might add. Oh, most of algebra. I forgot about the triple product. Yeah, let's talk about triple. So you can have you have two triple products. Um, you can have A dot cross C, because again, the cross product gives another vector, so you can then dot that with a third vector. And you also have the triple vector product, which is just A cross C. So the triple scalar product has a special property where you can kind of rotate out the vectors. So by that I mean if I just put everything one position to the left, that means that this is equal to B dot C plus A, also equal to C A. Just interesting problem. Triple scalar. And then there's a kind of mnemonic for this triple vector property. I've heard it called the back cab rule. And the reason why it's called the back cab rule, A cross B cross C is equal to B times A dot C. And again, keep note that this is still a vector because I have A dot C giving just a scalar coefficient multiplied by the vector B. So this is still a vector. Back minus cab. C times A dot back cab. And these expressions and these properties just so these will come up quite a bit when talking about like E and M, trying to do E and M problems. These are just very useful properties to have on hand. They'll simplify a lot of expressions that would otherwise be very complicated. And as you'll see way down the line, because I do want to build this up to give you guys a bit of a foundation when I talk about lasers. So when I eventually I want to talk about how the electricity and magnet so what's called Maxwell's equations. There are four main equations in electricity and magnetism called Maxwell's equations. And eventually I want to get to the point where I show you guys how we can prove that these equations allow for what's called electromagnetic waves to exist. This rule is going to come in back cab. All right. So that does it for vector algebra. Um, or at least the basics. Yeah. Um, so yeah, I want to start off fairly simple, algebra. Next week I do want to talk about vector calculus properties. Um, but I will give I'll try to give a little crash course on the important calculus properties, like what a derivative and then I'll try and motivate the little bit of yeah, I'll try and motivate the Calc 3 that you would need to get to vector calculus stuff. Um, so hopefully it still won't be completely foreign. Um, but yeah, so night, shorter stream.